In addition to working for Conservation Science Institute, I'm also assigned to the Aleutian Pribilof Islands Association as their senior scientist and energy program manager. Much of my work on energy is establishing renewable energy in Alaska's remote villages. My colleagues, Brian Hirsch of the U.S. National Renewable Energy Lab and John Lyons of a private company called Marsh Creek, LLC, and I are proposing a shift of using renewable energy more towards heating buildings in Alaska, and we would like to share this idea with our Russian colleagues. The paper is entitled, A Better Use of Wind Energy in Alaska and Applicability for Russian Villages. Alaska boasts 149 remote small communities, over 120 of which operate on independent microgrids, and most of the Alaska villages have a peak operating load of less than 200 kilowatts. Using wind energy to offset electricity produced by diesel in these communities requires a sophisticated integration of energy dispatch, electronic switchgears, storage, controls, and distribution to create a functional and efficient hybrid system. Alaskan customers of these electrical hybrid systems can suffer system shortcomings, including blackouts and sometimes increased costs to pay for these systems. Hybrid systems with energy storage can offer a level of stability and higher penetration of intermittent renewable energy systems than systems without energy storage. Such storage can be in several forms, including hot water and electrical storage. In Alaska, some hybrid systems using wind and hydro along with diesel are seeing great success, such as on Kodiak Island, Alaska. Though still young in its deployment in the field, the use of electrical energy storage, or EES systems, if properly designed and installed, can also increase grid reliability and reduce maintenance costs on diesel engines and wind turbines. For example, in the village of Kokanock, a remote settlement of 200 people located in remote Alaska, operates one of these microgrids with two reconditioned Vestas V17 turbines rated at 90 kilowatts each on 85-foot lattice towers. A synchronous condenser and grid-forming inverter are installed, along with 336 kilowatts of battery storage. Although some success comes from energy storage, another solution is to use the wind energy in real time to help offset the primary energy use in most Alaska villages, that of space heating. The Alaska Energy Authority has determined that about 55% of the energy used in Alaska villages is for heating homes and buildings. Using wind energy for space heating and heating domestic hot water can reduce integration and efficiency challenges associated with hybrid electrical systems and storage, especially in high penetration systems. Homes and other buildings, including heating insulated concrete slabs with hot water or resistance coils, the mass acts as a heat storage device that can release its stored heat to the building even when the wind turbine is not producing energy. The cost of using concrete floors can be cost effective when compared with more sophisticated systems. When properly constructed and integrated into the overall system, heating floors in cold climates has some promising applications because its thermal storage and slow release characteristics. For example, a newly poured concrete foundation could be poured on polystyrene board, isolating the floor and insulating the floor from heat loss to the ground, and embedding PTEX piping or resistant heating in the concrete. Once connected to the wind-producing energy source, the concrete floor would heat and become warm when the wind blows and the turbine is operating, and begin cooling when the wind is calm. But the floor would retain its heat in the mass of the floor for long periods. If the wind resource is especially good, The wind system can be sized according to allow for high penetration and the conventional diesel grid, and by using heat production and thermal storage, high electrical integration and storage costs can be avoided by direct conversion to heat and thermal mass instead of just electricity for the grid. A wind thermal system for the government facilities in Cold Bay and King Salmon, Alaska are models of low to medium penetration with coincident thermal energy generation wind due to locations having strong wind resource and the opportunity to optimize system economics through a significant offset of heating fuel consumption and electrical energy. In the low to medium penetration design, it is anticipated total wind generating capacity may meet the facility's peak power demand and heating fuel requirements. Through such a configuration, the wind turbines will provide a significant heating fuel offset by supplementing the thermal requirements, converting wind electric energy to thermal energy. The primary building blocks of the Cold Bay and King Salmon hybrid wind systems include wind generation equipment, microprocessor-based sensors that simultaneously monitor instantaneous load and wind speed, specialized controls that allow for seamless operation between the electrical grid and thermal-electric nodes and hot water storage tanks with associated energy delivery infrastructure as electric boiler system and energy storage. In the typical Alaska Village Microgrid Connect wind energy system, the electric utility must continue to supply energy regardless of wind speed and wind energy contribution. Here the wind generators run in constant parallel with the utility, which serves to reduce the electric load at the facility. This configuration produces no co-generated byproducts such as hot water, and there is no excess energy. By integrating wind turbine generating capacity to achieve energy conservation as an aggregate of all energy, as well as simultaneous production of beneficial thermal, our conceptual design produces far greater total energy avoidance in terms of fuel savings and superior long-term total system operating efficiencies. Accordingly, this design is focused on the low to mid penetration model, with thermal-electric integrating thermal storage nodes as its first priority use of wind energy. Secondarily, wind-generated energy will be used to offset electrical energy consumption. Russia has over 100,000 villages, and the Department of Renewable Energy of the Russian National Electric Utility has identified 17 specific regions out of 89 total in Russia where it believes wind energy development is particularly viable. And I won't name all of those villages and those regions because it challenges my Russian. But also the regions are listed in the paper. In 1997 through 1999, the U.S. Department of Energy and the Russian Ministry of Fuel and Energy worked together on hybrid wind diesel power systems. The National Renewable Energy Laboratory supplied technical assistance to the project, and the U.S. Agency for International Development provided funding for the equipment and supplies. It may be time to reestablish a U.S.-Russian wind energy program using new technologies and the strategies discussed above to provide electricity and heating to remote Alaska. Thank you, and again, you are welcome to contact me with comments or questions. Goodbye.